Hello, everyone. In Chapter 6, we study confidence intervals. In Section 6.1, we look at confidence intervals for the mean with large samples. Turns out the magic number is n is greater than or equal to 30. So if n is greater than or equal to 30, or when we know sigma, and the population is normally or approximately normally distributed, we're going to be using sometimes what's referred to as the Z distribution. What we're entering into now is a branch of statistics called Inferential Statistics, where we're going to use sample data to estimate the population parameter. And so the first thing to consider is a point estimate, and that is just simply the sample mean. So that gives us an idea of the distribution, and then we form an interval estimate, so a range of values, which is our estimation for the population, and it may or may not contain the value that is in the population. But theoretically, we first consider the level of confidence, and it's the probability that the interval estimate will contain the population parameter. And the larger the level of confidence is, the wider the interval. And we use Z sub C to represent what we call the critical values. And here's a little sketch of a normal distribution with the z-scores, and an interval is shaded. This is actually negative Z sub C on the left. And here we're seeing an example where we want to find the critical value Z sub C to form a confidence interval, given that the level of confidence is 0.88, or you could think of that as 88%. And there is a formula, but I'll just show you intuitively how to realize how to find that z-score. If we drew the distribution and we consider the mean of z equaling 0, and let's say this is our positive z and our negative z on the left, what we're saying is that there's 88% of the data in that interval between negative z and z. So I'll call it 8800, because that's an area, and what we're going to end up doing is looking up that area in the guts of the table. And to determine the z-scores, or what we will work off the left z-score. And so what we want to determine is that left cumulative area. And since we have symmetry between negative z and the z-score of 0, there's 0.4400 in this case, half of 88%. And knowing that to the left of the mean is half, or 0.5, the area that we're looking for is going to be 0.5 minus the 0.44, or 0.06, and I'll add 2 zeros to that. So that's the area that we want to look up in the guts of the table. And so if we look in the guts of the table for 0.06, we find that it's right in between 0.0594 and 0.0606. So recall from the past that when it falls exactly between, as it does in this case, we're going to split the difference. So it's between negative 1.55 and negative 1.56. So we'll use negative 1.555. So our z-score, we'll say, is plus or minus 1.555. Now, note that there is a formula. It's not actually in your formula sheet, but it is in the reading of the textbook. And the formula that they give, okay, I intuitively showed how you could determine to look up 0.0600, but the area is given by 1/2 times 1 minus c. So for our case, for c equaling 0.88, we would have that area is 1/2 times 1 minus 0.88, and 1 minus 0.88 is 0.12, and half of that is 0.06. So we get the same value doing it that way. Which is really just thinking about it as finding first the area in both tails. That's the point, the difference between 1 and the confidence interval, which would be 0.12, and then dividing that in half to get the area in this tail. So you could think about it either way, or literally just use the formula. So that's going to be your choice. But note that at the bottom of Table 4, there are critical values for some of the commonly used confidence levels. So if you look at Table 4, excuse me, on the first page, you can see that these are critical values for some of these most commonly used critical values. If you have a value other than this, then you're going to have to use the formula we just talked about, or the procedure that we just talked about. But obviously, if we're using one of these, 0.8, 0.9, 0.95, or 0.99, we can just get that z-score off the table quickly. So the majority of the questions will actually use these, but there will be an occasion where you will be asked to find the area for, or the z-score for a confidence level that is not one of those special values. So when we talk about the margin of error, that's the greatest distance from the point estimate to the population mean. So here's a number line, and it says find the sampling error. So we denote that by E. So that's just going to be the difference between, this is basically E, right? So the difference, let's say, between the mean of 11.4 and the sample mean of 9.2. So we get 2.2. Okay, going to the next page, we have a formula for that margin of error. And we say that E is equal to Z sub C, the critical value, times sigma, the population standard deviation, over the square root of n. And we're going to use this formula when either n is greater than 30. Oh, but something to note, I suppose, here, though, is when n is greater than 30, the sample standard deviation, S, can be used in place of the population standard deviation. So, in example 3 here, we want to find the margin of error for this given situation. C is 99%, or 0.99. So from table 4, we say at the bottom, Z sub C is given. That is, 0.99 is one of these special percentages, which is 2.575. Now we could go through the procedure if we want of taking 1 minus 0.99 and then half of that and looking up that area, but obviously much easier just to use the givens. So 2.575. Okay, so then the margin of error is given by the formula Z sub C. We could replace the sigma with an S over the square root of n. And that would be the 2.575. I always put parentheses here, you don't have to, but times S was 4.4 over the square root of n was given to be 53. So make sure you can calculate that. I'm going to choose to round it to 3 decimal places, so approximately 1.556. So double check and make sure you can do those calculations. So then we form the confidence interval. And the easiest thing to do, and these formulas are on your table, the easiest thing to do is to consider that the confidence interval for the population mean, we're always trying to estimate this population mean mu, is going to be between the point estimate minus E and the point estimate being x bar, the sample mean, and at the right end point is going to be the point estimate plus E, and there's our formula for E. So that's the easiest thing to do, is to use this formula for the population mean as an inequality with a left end point and a right end point after we find the value of E. And this is given on our table as well. So you can see in the table, there's the formula for the inequality, estimating the population mean mu, and here's our formula for the margin of error. And it tells us that we're going to use this when sigma is known, sample size is random, population is normally distributed, or we've got this large sample size greater than or equal to 30. But then it mentions this about, and notice that instead of Z, it uses T. And this is when sigma is known, or sigma is unknown, excuse me. So if we know sigma, generally we're going to be using Z. But if sigma is not known, and the population is normally distributed, or n is greater than or equal to 30, then we're going to have to use T. So we'll be talking about that in section 6.2. So for now, let's take a look at this. For the margin of error example 3, find the confidence interval for a sample mean of 5.3. So all that we're talking about doing here, we're kind of leading you up to just doing this in little pieces to lead you up to the big picture. But the sample mean is 5.3. We want to find the 99% confidence interval, which corresponds to the margin of error we just found. So therefore, x bar minus E is going to be the left end point, and the population mean mu is going to be greater than that and less than x bar plus E, which is going to be the right end point. So we'll just substitute x bar 5.3 minus that population, or excuse me, the margin of error, 1.556, is going to be less than the population mean. So you always want to leave mu, okay, as your population mean in the middle here, because that's that is what we are trying to estimate, and that's going to be less than the 5.3 plus that margin of error of 1.556. And so then that gives us a left endpoint of 3.744, which is less than the population mean, which is less than 6.856. Now we could report this as an interval. If you want to report it as an inequality, I think that's actually nice to do it that way, but as an interval, using interval notation, parenthesis, left endpoint, 3.744, separate by a comma, and the right endpoint of 6.856, and then close our parenthesis. So either interval notation or as an inequality is going to be acceptable, but be careful. In my math lab, sometimes they ask you to do both, and of course, or one or the other, and of course pay attention to the rounding. Alright, so here they want a 95%. This is kind of putting everything together, given all the information. That is, given the sample mean, the standard deviation, and the sample size. And we want to find the 95% confidence interval. So if C equals 95%, that's 0.95. From table 4 at the bottom, once again, this critical value is given. So just to show you once again, this is the first page of table 4, the negative z-scores, and at the bottom they even draw a picture for us, and 0.95 confidence level corresponds to 1.96 as the z-score. So z sub c is 1.96. And then we have to calculate the margin of error. And the margin of error is given to be z sub c times sigma over the square root of n. So everything's a given here. Now that we know z sub c is 1.96, we have 1.96, and then the standard deviation was a given 0.5, so times 0.5 over the square root of the sample size, and that was also given here to be 84. Okay, so then we just crunch that down. I'm going to round to 3 decimal places, and we get 0.107. So now for the confidence interval. Again, I always like to write the formula. X bar minus e is less than mu, which is less than x bar plus e. And we are given the sample mean x bar was 7.7. So therefore we'll have 7.7 minus e is 0.107, which will be less than the population mean mu. Again, we always want to leave mu in the middle because that's what we're trying to estimate. And we have the left end point, and the right end point is going to be the sample mean of 7.7 plus that margin of error. I don't know why I wrote the number 4 there. That should have been the letter E. Sorry about that. And so plus that margin of error, 0.107. So therefore we get left end point 7.593 is less than the population mean, which is less than right end point is 7.807. Or once again, interval notation, we use parentheses because we're not including the end point. So 7.593 left end point, comma, to separate the left end point from the right end point, which is 7.807, and then a parenthesis again because it's strictly less than and strictly greater than, meaning endpoints are not included. Okay, here's our interpretation of a confidence interval. A lot of times people say the wrong thing. People say that you're guaranteed that 90%, you're 90% confident that the mean lies between these two values. That's what a lot of people say, which is really wrong. Because what it really means is that if you formed an infinite number of confidence intervals, 90% of them would contain that population mean. And here's an example of what I just said. So when you construct a confidence interval, it doesn't mean that the population parameter mu is actually in there. It's either in the interval or it's not. Okay, so it could be outside the interval. So for example, if the level of confidence is 90%, it means if we take a large number of samples, that's what I meant when I said an infinite number of samples of the same size, and construct an infinite number of confidence intervals, or construct a confidence interval for each of those infinite number of samples, 90% of them will contain this population mean. For example, in this little sketch here, we've got mu, which is the population mean running down the middle. And these lines all represent the confidence intervals. The points on the line represent the point estimates for that particular sample, which are the X bars. And notice that the points are different for each of the confidence intervals because you're taking a different sample, so you're going to get a different sample mean. And the line segments, those are the confidence intervals. And theoretically, what we're saying is that if the confidence level is 90%, then if you create an infinite number of confidence intervals, I'll just abbreviate that as CI, then 90% of them will contain the population parameter mu. So you could see that in this little sketch, all of these that hit that dotted line of mu contain them. This one actually right here, this one missed. Missed in quotes. Okay. So theoretically, you don't really need to worry about that when you go through the mechanics, but that idea actually will come into play when you do the next project, and hopefully you'll see the connection. Alright, so now some examples. Word problems. And so we have a college administrator wishes to estimate the mean age of all students currently enrolled. He's got a random sample of 35 students. There's the mean age. So this random sample, let's go off to the side here and write down our givens. Random sample of 35, so n is 35. Okay, this is the mean age of this sample. So therefore, the mean of a sample, recall, is X bar. And that's 22.9. So recall that we'd drawn this table earlier for a population and a sample, if we're talking about the mean, we use mu for the population and x bar for the sample. And also, just to mention, if we're talking about the standard deviation, we use sigma for the population and s for the sample. So that's our sample mean, because it mentioned in the reading in that sample of 35 students, that was their mean. So that's the sample mean. From past studies, whenever it says past studies, that's population. So sigma. Because past studies, the standard deviation was 1.5. And so sigma is 1.5. And we're also told that it's normally distributed. And we want the 92% confidence interval. Now, first off, there's actually a flow chart that I'm going to let you use on the final exam. You'll be sent an email as to where you can find this. There's a new flow chart in the textbook, but this one I like the best. This flow chart tells us when to use Z or T. Now, obviously, we're just studying the Z distribution, so this would be an example involving that. But notice that it first asks, do you know sigma? If you know sigma, which we do, immediately we're going to use Z. Okay? If not, we're going to have to explore the other characteristics. But right away, this tells us that since we know sigma, we're going to use the Z distribution. Okay? And so, once we decide what distribution to use, and we'll see the differences later on, of course, when we start talking about the T distribution, then we proceed. Now, unfortunately, 0.92 is not in that list on table 4. So therefore, we've got to go through that procedure. So see, it's not in here, 0.92. So we've got to go through that procedure where we draw the distribution, okay, and on either side of Z equaling 0, there's our critical value Z sub C and negative Z sub C. So this is for C equaling 0.92. I might actually put it over here. C equaling 0.9200. I'll get rid of this, and the reason why I want to get rid of that is because I want to draw a left cumulative arrow here. If the whole thing is between negative Z and Z, between negative Z sub C and Z sub C is 0.92, then this area is 0.4600, and subtracting that from 0.5, we get 0.0400. So therefore, Z sub C is going to be, so we look up 0.0400 in the guts of the table. So 0.04, okay, it looks like it's closest to 0.0401. So remember, we take the closest one, unless it splits it in half, like we saw earlier. That looks like negative 1.75. But we'll always take Z sub C to be a positive. You could say plus or minus, but the point is we're going to be calculating the margin of error and then subtracting it from the mean and adding it to the mean, so that takes care of the plus or minus. Now, alternatively, you could have used the formula 1/2 1 minus c to get this area of 0.04. And 1/2 times the quantity 1 minus 0.92 is 1/2 of 0.08, which is the 0.04, and then add a couple zeros if you want. And then you would look it up and find, of course, C sub C is the 1.75. So now we're ready to go. We first calculate E, and E is Z sub C times sigma over the square root of n. So now we have 1.75 times sigma 1.5 over the square root of n was 35. And that gives us 0.444. So now our confidence interval, again I'll just use CI, is going to be left endpoint x bar minus e is less than the population mean parameter of mu that we're trying to estimate, which is less than the right endpoint of x bar plus e. And so we just plug in x bar was 22.9 from the given right here, and then minus e, which was 0.444, what we just found. It's going to be less than the population mean mu, which is less than the x bar of 22.9 plus that margin of error, 0.444. So therefore, left endpoint crunches down to be 22.456, which is less than mu, which is less than the right endpoint of 23.344. Okay, I think I'm going to stop this video here. We'll do a part 2. There's one more problem to look at and then another concept. That'll be a short part, but I think better than making this video last an hour. We'll stop this video here and we'll do a part 2 when you're ready.